better to listen, you can, by all means, just listen to the presentation. All right, I'm going to expand my screen to show the PowerPoint, and we'll talk about the atomic model. If you have a question, you should have a little hand at the bottom. You can raise your hand. That will signal me that you would like to speak. I will take it off the microphone, and you're allowed, and then you'll see it green down at the bottom. Right now it says busy, and it's kind of an orange-red color. But once it turns green, you can click the button and speak, or you can type information into the chat box. And yes, I will record this. In fact, I'm recording it right now. And then in a day or two, it will be uploaded in your class. Okay, so some of you may have been familiar with this. It may have a lot of knowledge, but just to make sure, I want to start from the beginning. What you'll see if you look on your screen is an example of what we call the Bohr model of an atom. What it has is a nucleus. The nucleus contains protons and neutrons, and electrons are kind of spinning around in orbits. Oh, Ernesto, I see oh, there you go. You had a sad face next to your name. There's electrons that are spinning around the nucleus. And where those electrons are, where those orbits are, depends on how much energy that electron happens to have at that time. So over time, the atomic model, so we're talking about atoms, has changed throughout the centuries. So in 400 BC, it looked like just a round ball. And over time, different scientists had influence over what we now think of what our atoms look like. So our first person of note is a Greek philosopher that thought about if matter, so if something, can you divide something over and over and over again, or is there a limit to how many times something can be divided? So can you constantly or consistently divide something in half forever, or is there a limit to how small something can be divided? His theory is that matter cannot be divided into smaller and smaller pieces, but eventually there's something, the smallest piece would be obtained. He thought this piece would be invisible, and he named it atomos, which means it cannot be cut. So that's where our the name atom comes from. So these were some very small particles made of the same material. They were different shapes and sizes. There was an infinite number, which means that they're always moving and joining together. So this was the original thought, or the first idea of the atom. So now he came up with this, and then it just kind of got brushed by the wayside, and it was forgotten. So completely forgotten about until 2,000 years later, the idea started to arise again. And Aristotle and Plato had the idea that there were basically four building blocks of life, which is earth, fire, air, and water. Their ideas, because they were very respected, this idea was more prominent in the scientific community versus the small indivisible atoms. We'll get to that. So next, Dalton performed a number of experiments to help lead to the acceptance of the idea of atoms. He thought that all elements are composed of atoms. Atoms are, again, indivisible and indestructible. We do know now that we can actually break atoms chemically, but physically you can't separate an atom. Atoms of the same element are exactly alike. So this is a new theory. So originally it was that elements had all different shapes and sizes, or atoms were all different shapes and sizes. like a carbon atom was a different shape than the next carbon atom. But Dalton's theory is saying that all atoms are the same, of the same element. If it's a different element, he proposed that the atom would look different. And a compound, this is where we come up with the word compound, that's from Dalton's theory that they're formed by the joining of two or more elements. So this theory then, in the early workings, became one of the foundations of modern chemistry. So this is kind of where everything gets started. So now a new scientist came along in 1897. So this is about 130 years ago. He developed through a series of experiments that an atom is not necessarily the smallest form, but it actually is made up of even smaller particles. And his theory is called the plum pudding model because it's a big round positive ball that has the electrons kind of sticking on top of it, much like what at the time was a very popular dish, which is plum pudding, which is kind of like having pudding with raisins scattered about. Sorry, is this bothering you? Okay. Yeah, absolutely. You can learn about atoms. It's kind of dry. Not gonna lie. So the way that he determined that there was actually smaller pieces inside the atom was because he used this particular experiment and he had a electric current that passed through a glass tube. And in this glass tube held a certain gas. And when the electric current passed through, it gave off negatively charged particles, which in turn ended up changing color and being attracted to a certain piece on that tube because you had a positive end and a negative end. So he had a gas tube, sent an electric current through it, and this is how he discovered that there were positive and negative pieces that made up this model of an atom. By the way, that's I believe one of your test questions will ask you to compare and contrast different experiments that these scientists came up with. So this surprised him, and because the gas atoms were uncharged, so there was no charge in the actual gas in the tube. So the question was where those negative charges came from. He concluded that they must have come within the atom, so a particle smaller than an atom had to exist. So that is saying, okay, we can devise an atom even smaller than its piece. He called the negatively charged corpuscles, but we call those electrons. Since the gas was known to be neutral, having no charge, he reasoned that there must be positive charges in there as well to balance the negative charges that he pulled out, but he couldn't find them with his experiments that he did. So the next came along. This is the most famous experiment. You'll hear a lot about Rutherford's gold foil experiment. So about 15 years later, maybe a little less, Ernest Rutherford was working on an experiment looking at the atomic structure. He took and fired a stream of very tiny positively charged particles at a sheet of gold. Very, very thin sheet of gold. And most of the positively charged particles passed through the gold sheet without changing at all. So they went straight through the gold sheet, which is what he expected. But what he didn't expect was that some of these charges bounced away as if they hit something. So he knew that positive charges repelled positive charges. So to him, what he's saying is there's a lot of space where these positive these positive particles can fly through the gold sheet, but at some point in time, in some of those spaces, they were repelled and bounced off this gold. So because positive repels positive, he was able to determine that atoms were mostly empty space, or that the positively charged center of an atom is only taking up a very small piece of that atom. And that's where those particular charged particles ended up hitting, was the center of an atom. So here's actually what the experiment looked like. He had receptors all around the gold foil to measure where those charged particles were, the path of those charged particles. He had the beam of alpha particles kind of fired through and hitting the gold sheet, and you can kind of see how some of those particles actually bounced off the gold and didn't follow the normal trajectory. So again, his experiment, so the gold foil experiment, proposed that atoms were mostly open space, that atoms were not just a whole positive mess with electrons kind of sticking all over it. He concluded atoms had to be very small, have a very dense positively charged center that repelled his positively charged bullets. So he's the one that came up with the idea of the nucleus, and the nucleus is very tiny compared to the whole of the atom. So again, this is a test question that you will see. One is to describe Rutherford's gold foil experiment, and two, what that means in the idea of the scientific theory. Okay. So what he thought is that there was a center, positively charged center. The electrons are kind of scattered around that center. So just a few years later, so 5 years later, Niels Bohr proposed a little bit of an improvement on Rutherford's idea of an atom. And he put electrons in specific, what we call energy levels. Okay, if you think about if you're standing in a center and you're holding on to somebody with one hand and you start to spin around, and then you add two people to your circle and you're in the center and you're spinning two people around. Well, the person that's holding on to you, it takes less energy for them to hold on to your spinning circle is the person next to them. So the person on the outside, it's going to take a lot more energy for them to hang on as you're spinning around in the circle. Same thing if you keep adding more people. Okay, the further out, the more energy it's going to take for them to stay connected to your constantly spinning circle. So Bohr took this information and applied it to electrons. So electrons closest to the center need less energy to stay in their orbit as the electrons that are further out. Okay, we have kind of built upon that and came up with there's an electron cloud model, and now we have the wave model. So what we're looking at is the principles of wave mechanics. So according to the theory of waves, electrons don't really move about in a definite path like an orbit, but they are generally in what we call the proximity of where we expect them to be. So it's kind of a probability, like it probably 90% of the time would be in this particular space. It is impossible to determine an exact location of an electron. So again, it's the probable location based on how much energy that electron has. So again, moving into electron cloud, where we're looking at how much energy an electron has to the probability of where it would be within that space. So electrons, again, to reiterate this point, electrons with the lowest energy are found closest to the nucleus. The higher energy are further out from the nucleus. So here is just a summary of this. The Greek philosophers and Dalton thought that the atom was indivisible, which means that it couldn't be divided any further. Thomson on down came up with the theory of electrons and kept the electrons. Rutherford discovered the nucleus. Bohr then added the orbit, and now we've moved to a sort of cloud of electrons rather than a specific pattern. So that kind of gives you the timeline of how we've developed our atomic theory. Okay, I'm going to move on. What's a Bohr? Bohr is Niels Bohr. So he was a scientist. And so we use Bohr's theory, or Bohr's model is what we call it, because he's the scientist that developed that particular structure of having a nucleus in the center with the electrons kind of floating around like planets orbit the sun. Okay, so now I'm going to look at the atomic structure, the actual structure, and how we look at that on your periodic table. So we have three main pieces of an atom. We have the electrons, protons, and neutrons. We've come to discover that there are actually a couple hundred different particles inside of a nucleus of an atom. There's quarks and neurons and all other types of particles that they've discovered. But the three main are electrons, protons, and neutrons. Electrons they are a negatively charged particle. They have a charge of -1. Their mass is 1/1820th of a proton. So it's 1/1820. So we actually do not include that in our mass calculations because it would take 1,820 electrons for it to equal the mass of one proton. So when we are looking at calculations of an atom, electrons do not actually include any mass, so to speak. And the location of electrons are in that electron cloud, so they're kind of floating around the nucleus. Next, you have protons. Protons are a positively charged particle. They have a mass of 1, and they are located in the nucleus. And then neutrons. Neutrons do not have a charge. They're neutral, and they are also located in the nucleus, and they weigh about the same as a proton. And if you look under the particle section, it shows you what symbols we use for each one of those particular particles. So electron has an E with a little negative sign. Proton is a P with a positive sign, and then neutron, we have an N with a little 0 that's next to it. So now we look at, on the periodic table, there is an atomic number of an element, and every element has its own specific atomic number. That atomic number relates to the protons of an element. So for instance, carbon has 6 protons. It is atomic number 6. Phosphorus has 15 protons. Its atomic number is 15. Gold has 79 protons. Its atomic number is 79. So the atomic number, which is usually listed in the top left-hand corner of the periodic table, is representative of how many protons an element has. If you change the number of protons in an element, it is no longer that element. It becomes a new one. Okay, so for instance, hydrogen has an atomic number of 1. If I change the number of protons to 2, I no longer have hydrogen. It now becomes helium. So again, the protons are the atomic number. The protons designate the element. So most of the time when we're looking at the periodic table, we are assuming that an element is neutral. So think of a positive and negative. If you have a positive and a negative and combine them, it has no charge. It is neutral. So if it has 11 protons, which is 11 positive charges, it's okay to assume that it has then 11 negative charges or 11 electrons. So the atomic number represents both the protons and the electrons of an atom. In each box, it also includes what we call a symbol. A symbol, the first letter is always capitalized. Second one, if it has it, is lowercase, and that symbol is specific to each element. Next, underneath the symbol is a number. This number is what we call the mass number or the atomic mass number or the atomic mass unit. It is a relative term, which means that we have designated that one atomic mass unit is equal to 1 gram. But what we're saying there is that atomic mass is equal to the number of protons and neutrons that happen to be inside a nucleus. Sometimes you will see the atomic number being with a decimal. What we do is we just round the atomic mass to the nearest whole number. So for instance, oxygen's atomic mass is really 15.99, but we're going to round that up to 16. What that means, that atomic mass, if we go back to original screen, I think it was screen 2, you'll see that protons and neutrons each equal 1 mass. Which means that if oxygen is number 16, it has an atomic mass of 16, it is element number 8 on the periodic table. That tells us that there's 8 protons. It also tells us that there's 8 electrons. But then the atomic mass will give us an additional piece of information. It's telling us that the mass number, or the atomic mass number, is 16. So if we have 8 protons, that means that there must be 8 neutrons as well, because the protons and the neutrons are equal to the mass number. You just want to check in to make sure that that makes sense, because this is a big piece. Does everybody understand how to determine the number of protons, neutrons, and electrons in a mass number, given a mass number and an element number? So I'm going to give you an example. And then just give me just 1 second here. Okay, so I just sent out a poll. So if I had a element that had an atomic number of 6 and a mass number of 18, what are the protons, neutrons, and electrons in that particular element? So choose your answer. Perfect, Trevor. Thank you. Really, I don't have an answer from you yet. Oh, perfect. I do. Great. Nice job. Yes, it is 6 protons, 6 electrons, and 8 neutrons. Perfect. So you guys got this. Okay, so summarize. Number of protons, number of electrons is the atomic number. The mass number is the protons plus the neutrons. To figure out the neutrons, you take the mass number and subtract the number of protons. Okay, so we have some information now. We're going to take this a step further. An ion is what we call an atom that has a charge. So we have elements. We normally think of them in their neutral form on the periodic table. But when we have a charge attached to them, we call it an ion. So we can't change the number of protons, right? Because if we change the number of protons, we are changing the element. So what will happen is our electron number will change sometimes. And if our electron number changes, it will change the neutral atom into an ion. We have 2 types of ions. Although the spelling looks a little strange, they are actually pronounced, the first one is pronounced an anion. So think of it with a hyphen between the N and the I. So an anion. An anion is something that has a negative charge, and which means that it has more electrons than it does protons. So it's gained electrons. We have another type of ion that's called a cation. So again, a little hyphen between the T and the I. A cation is an atom that has lost its electrons. So there's more protons now than there is electrons. We can't change the number of protons, so it didn't get additional protons. But it lost some of their electrons, so now we have an imbalance. And a cation, I think of it as like a cat has paws. This is how I remember the two. A cat will have like paws, so cation with a positive charge. Okay, so for example, oxygen has an atomic number of 8, which means it has 8 protons and 8 electrons. So an ion of oxygen would be oxygen with a -2 attached to it. So what that's saying is that it has gained 2 electrons. So now it has more electrons than it does protons. It's no longer neutral and it carries a negative charge. So when this happens, we call these are isotopes. Isotopes are a little bit different than the ion charges. They have to do with a different number of neutrons. So we have neutral atoms that are on the periodic table. We have ions, which are a difference of electrons. And now we have isotopes, which is a difference of neutrons. So they are the same element, they just have different mass numbers because they have different neutrons. Remember, protons don't change because if we change a proton, it changes the element. So when it has a different number of neutrons, it is what we call an isotope. So for instance, chlorine, here we have chlorine 35, which means it has a mass number of 35. The protons is 17. And then you also have chlorine 37, which means that it has a mass number of 37, but the protons are still 17. So an isotope is a difference of neutrons. These isotopes are very similar because they have the same number of protons and electrons. So the neutrons may vary a little bit, but the element is pretty much the same. So here's an example of hydrogen. Hydrogen, there's 3 actually types of hydrogen. We have hydrogen 1, hydrogen 2, and hydrogen 3. All 3 of these are found in nature. The first one has one proton and one electron, but it has no neutrons. The second one has one neutron, and the third one has two neutrons. And these are all elements of hydrogen. They all exist in nature, but they just vary in the number of neutrons. So what you see on the periodic table with the atomic mass number, that's kind of an average of all the different types of isotopes that are found in nature. So again, here's an example. You have the mass number, the atomic number, and the mass number is the average of element masses that are found in nature. I don't think you guys need to do this in yours, so I'm going to skip it. All right, so we're good. The way that they've determined how that average is found in the atomic mass is by looking at what the percentage of each particular isotopes found. So, for instance, for carbon-12 is the most abundant, so 98% of that's found in nature. But there are some isotopes that are out there. One is carbon-13 and one is carbon-14. So what happens is they take the average of all three of these percentages to come up with the atomic mass for that particular element. And that's what you see on the periodic table. So I am done with this. I want to make sure that you guys are okay with your assignments and what the expectations are for those. If you have any questions, this is a great time to ask. And if you have any questions about the material that we covered. If you have no questions, I'm done. You can log off. If you want to stay and chat and have questions, feel free to either take the mic and use it, or you can put something in a public chat box. If you take the mic, just remember that it is broadcasted to all members, all parties that are here. So Ernesto, great question. When you log on for the lecture, I get a report of who's attended, and then I use that report to score you for participation for the lecture. So for this particular assignment, you won't need to turn in anything. I will take care of that. If you guys don't have any other questions, I really appreciate you taking the time to come to this particular. I know it does take time out of your day to schedule, and I really appreciate you showing up.